So, good morning, everyone. So today I want to talk about, we will talk about some of the applications of um, this linear operator theory in robotics and power systems. So I'll predominantly focus on the robotics, and also touch upon some power system because there are some problems which actually are like, the application actually will also be useful in robotics. Like the application I'm talking about is like propagation of uncertainty. So I'll tell you more about as when once we get there. The first application I want to talk about is actually how to use this to design safe controllers, right? So um, and I sort of give you some glimpse of it yesterday in terms of like how does this occupancy or the occupation measure sort of translate to safety, right? So we'll sort of go a little deeper on that. Uh, so safety using density functions. Okay. So before talking about this, let me just tell you uh, how mm, what what are the ways it is done right now, right? So maybe some of you are familiar, but maybe some of you are not familiar with. For just for those who haven't seen this before, so typically the problem is the following, right? So you have some initial state, let's say x0, and you want to go to some final state xt, okay, and then there is some obstacle sets that you want to avoid, right? So now you want to do this for a for a dynamical system of the form x dot equals f of x plus g of xu, right? So this is like, you can think of this as your robot dynamics. So there's a drift term, there's a control term, and so on. So you want to find a u which will take you from x0 to xt while avoiding this unsafe state, right? So typically what happens in robotics that you don't when it comes to a planning, so this is called a planning problem. When it comes to a planning problem, you don't necessarily deal with a complex robots equation, right? So rather than using these equations, you just design the path for a because it just you want to find a path, so you can just design it for some simple system like x dot equals u, or maybe you could have some dynamics, but I'm going to explain it in a special case of this so-called integrated dynamics, right? So these are the integrated dynamics. Okay. So of course there is variety of algorithms there for motion planning. A lot of them actually the algorithm which are more popular. These are actually some of uh, these are based on probabilistic methods. Okay, so they give you some probabilistic guarantees, and they've uh, at the heart of it they sort of build on the search. They are basically search algorithm. Okay, so they build a tree. So basically they grid the state space, they build a tree, and then they put a node and then keep on extending this. So imagine that you are in like a two space, so you can grid this space, and from every point you can actually grow a tree. So you keep on growing the tree until you reach the target. If you reach the target without seeing the obstacles, you are successful. If you hit a target, sorry, if you hit obstacles in this search process, then you stop because that's not a feasible part, right? So these are actually based on search, random searches. So I'm not going to talk about them. I'm going to talk about methods which are deterministic. Okay. Not only that, the method which will give you a control, feedback control. So I'll tell you what exactly I mean by feedback control. Now, the primal methods for motion planning and safety are based on, as I was telling you, this navigation function or a potential function. Okay. So what's the distinction between navigation functions and this potential function? So navigation function, um, potential functions. So potential functions are functions which are like a Lyapunov function, right? So how the Lyapunov function, you can think of them as a like generalizing the Lyapunov function in the obstacle. So what the Lyapunov function looks like? Lyapunov function, they have actually like an energy based interpretation. So they are zero or at the target set, and then they go to infinity as x approaches infinity, right? So you're basically um, trying to find a so if in for this system or for this system, you're trying to find a control input u so that you actually the Lyapunov function is decreasing along the trajectory so that eventually you'll get to the target state, right? Now imagine you actually modify this Lyapunov function in such a way that wherever you have an obstacle set, you actually make this function very large, okay? Because you are actually moving with the, so let's say v is that a potential function, okay? So then let's say if I'm working with a simple x dot equals u dynamics, then you design u to be minus partial v partial x, okay? So you're going in a negative gradient of the v. The goal, the objective is to find this function v, okay? And that's the difficult part. Objective is to find a function v so that when you go along a negative gradient of this function, potential function, then you'll reach the target while avoiding the unsafe set. Okay, so now think about the following, right? So now if you want to reach the target, then you want to have the minimum of the v at the target set, right? Because that's where there's a negative gradient. That's where you will try to go. That's the direction you'll try to go because you're taking a negative gradient. And wherever you have the unsafe set, you will try to make the v very large. Potentially, you want to make v to go to infinity, right? So the function v have v of x is minimum at x equals to target, and v of x is maximum or infinity at x belongs to some unsafe set O. So let's call this set O for the obstacle set. Okay? So this will be the kind of typical construction. But the challenge is that, right? But the challenge is that just because of the topology of this problem is that when you do something like this, you will actually introduce undesirable minimas. And now see what happens if you have a so undesirable minimas will be like critical points. So that means the gradient of the v at that point will be 0. So if that happens, then the v, although it has a global minima at x equal to 0, which is, sorry, x equal to target set, which is the point that you want to reach, but you will introduce some new minimas, which are local minimas, okay? And when you start to move with this u, you could get, instead of getting to the global minima, you could get to the local minima, okay? And then you get stuck there. You cannot get out of that. Okay? So that's a challenge in terms of constructing this so-called potential function. Okay? Now, the navigation functions are the one, of course, just like in the Lyapunov theory, we know that there exists a Lyapunov function. The problem is actually we don't know how to find the Lyapunov function. So existence is of the Lyapunov function is known. Similarly, one can also say that there exists a potential function which will take you from the x0 to xt while avoiding the unsafe set. But the challenge is we don't know how to construct it. Okay? Now, for the case when you can actually find one, and that it is possible to actually find one, those are called as navigation functions. Okay? So navigation functions are the one which will guarantee to solve this problem. But the construction of a navigation function is again tricky. You don't know how to construct them, except for like very special cases. Okay? So these are the challenges with some of these existing deterministic methods, I would say, when it comes to the motion planning. Now, yesterday I gave you this dual way of looking at this problem, which has to do with the form the density, right? And so what is the okay? So let's say I give you x dot equals f of x system, and if you are able to find a density, so before actually even talking about a safety, let me just write down this because this is where we ended yesterday. So let's say if I have a density function rho which solves the following equation, okay? Rho of x is uh, is positive, okay, and rho of x. So what I'm going to show you in this today in this process is that how to construct this density function analytically, which will allow you to solve this planning problem. Okay. So before that, I'm just going to present, reiterate what we did last time, in the previous lecture, towards the end of previous lecture. Okay, and then tell you the physical significance of this little more here, little more detail. Okay. So rho of x is a positive function, and then rho of x is actually um, is maximum, or um, rho of x is well defined on everywhere except for the target set. Okay? Because rho of x will have a singularity at the target set. Okay? Now, if you have a function like this, and then rho 0 of x is some function which um, is bigger than 0 on um, or rather for all x in a small neighborhood of the x0. Okay? So since I want to go from initial set to the target set, where my initial set is at x0 and the target set is at xt, I, I construct a ball around this x0, and I can define a function which is positive on this ball and 0 outside. So for example, you can take rho 0 of x to be, let's say this is n, neighborhood n of x0. So I could take rho 0 to be 1 n of x0 of x. So what this is the indicator function of the set n0. Okay. So you have a function which is 1 in a small neighborhood and is 0 outside, right? So that's the construction of the rho 0. Now, if you actually solve this for some positive rho, then this rho actually has some nice physical interpretation. So rho of x is a occupation density. Okay, that means the occupancy of any set A in Rn minus some small neighborhood of x of t is given by mu of A equals rho of x over A dx. Okay. So what does this mean? So this means that, roughly speaking, okay, because I'm like the so if you want to look at the amount of time the system trajectory spend in any set A before actually reaching this target set xt, starting from initial set around x0, is characterized by this number. Okay, is characterized by this mu of A. So if mu of A is 0, that means almost all. So I think there are, if I want to say it precisely, then almost all initial condition starting from almost all trajectories starting from the initial set x0 will spend 0 time in the set A. That doesn't mean that there may be a 1 or 2 trajectories which may actually pass through the set A, but those trajectories are one or two. That means they have a measure 0 set. So most trajectories, almost all with respect to Lebesgue measure, um, they will not pass through target set. So they will not pass through the unset set. That means they have 0. So that's the main starting point for the construction of density function. Now, how do you construct the density function? Clearly, if I want to make this occupancy in the unsafe set O to be 0, then I have to pick the rho. If I want to construct the rho now, I can pick the row such that row is 0 on the unsafe set. Okay? So that's the construction of row is as simple as that. So you just make the row 0 on the unsafe set and make the row take large value at the target set. Okay? Maximum value at the target set. And then we can show that this row can be used for designing controllers. And now, so in the navigation function case, when you have something like x dot equals u, right? What did you use? You use u to be minus gradient of this. Okay. Now, in the density function case, you use, let's say I construct this density row, you use u, instead of going in the negative direction, you will go in the positive direction of the gradient, positive gradient. Okay. So you choose your u to be partial rho, partial x. Okay. Because it is doing exactly opposite, right? So where the v was large at the obstacle set, my rho is 0. And where the v was minimum at the target set, my rho is actually maximum. So instead of going with the negative gradient, I had to go with the positive gradient. Okay? So let's see how to actually construct such a row. I mean, how do you actually provide a smooth construction of such function? And so one of the challenge with this solving this navigation problem is that in a simple, in a low dimensional state space, let's say 2-3 dimensional, you can actually do some brute force search, like which is what is done in the probabilistic methods to find to reach the target and avoid the unsafe set. But as the size of the state space grow, the dimension of the state space grow, this becomes a difficult problem to solve. So the motion planning problem is actually typically difficult to solve when you are trying to do it in a large dimensional state space. Like, for example, imagine you want to do a motion path planning for n-link robot, like the manipulator robot. So now you have n degrees of freedom, and then so you are really working in a very high dimensional state space. Finding that feasible path, there is no optimality here, right? So there's right now you're just trying to find a feasible path. We're not trying to find the shortest path, or we're not trying to find a path which takes minimum amount of energy or anything. We're just trying to find a path which will take me from initial state to the target set while avoiding the unsafe set. So that this feasibility problem is itself a very hard problem to solve as you go in larger and larger dimension state space. And that's why this is could be very attractive, because what we're going to do is actually we're going to give you a general construction of a density function that is independent of the state space dimension, or rather, this construction you can do it in arbitrary high dimensional state space. Okay, and the basic ingredient of this construction is simple. You just construct a function which is 0 on the unsafe set, and then maximum on the target set. Of course, now when you do this construction, we assume that we know where the unsafe sets are, right? So, but I'll tell you how to sort of extend this to the case when you don't have a global information over unsafe set. Okay, but let's first look at the case scenario where you have the knowledge of unsafe set. Of course, you can work with multiple unsafe sets, so you don't have to be single unsafe set. But right now, I'm just going to give you the construction for the case when this has only one unsafe set. Okay, and the construction is fairly easy. It's just, if you guys know how to manipulate functions, it's just you're trying to construct some smooth functions with like bump functions, which are 1, zeros, and some region, and so on. So let me just give that explicit thing. So let's say that the unsafe set I'm going to denote is, okay, we are using the O notation. So unsafe set is described using some function, let's say x in n, such that h of x is less than or equal to 0, right? So I'm describing this unsafe set using some function h of x less than or equal to 0. So think of the h of x for example, if you want to be a little more concrete, let's say if I have a unsafe set which is a circle around the origin, then you can take of radius r, then you can take x square plus y square minus r square less than or equal to 0. So your h will be h will be x square plus y square minus r square, right? So that will be your function. So this function will be less than or equal to 0 on the unsafe set, and it will be positive outside, right? So you can always do that. Okay? Make sense? So let me just say, for example, if O is something like this, R, which is, so this is basically x square plus y square minus r square, is equal to 0. So then you can take h of x, or sorry, h of xy. So maybe I should, or x1, x2. So h of x will be x1 square plus x2 square minus r square. Okay, so that will be your h. Okay, so that's your unsafe set. And now, what you will do is actually have an unsafe set, but there is some sensing region around the unsafe set, right? So there is unsafe set, but then the robot can actually sense the unsafe set. So that the sensing region, let's call it by script S, is denoted by Rn, such that S of x is less than or equal to Rd. So again, that safe, the sensing region is kind of, so is described using this function S. So think about, let's say this is your unsafe set, right? I don't know if you have different colors here. Yes. So then you can construct this sensing region around this unsafe, okay? So that the robot can just navigate freely if it is outside the sensing region, but as soon as they enter the sensing region, it can actually sense the obstacles. It can actually feel that. Okay, so and that sensing region is now described using S of x less than or equal to 0. Oh, sorry, S of x less sensing region, S of x less than or equal to 0 minus the obstacle set. Okay, so this S of x less than or equal to 0 will be the entire thing, and then you take away the obstacle set from it. So you subtract those two sets, and that gives you the sensing region, which is like sort of an annulus region in this example I'm constructing. Now you can now you can actually construct your row of x to be oops, divide by some v of x. What is happening? So row of x to be psi of x by v power alpha. So this is my construction. I'll tell you what the psi of x is, and what is v of x is. Okay. So what is the psi of x? So psi of x is a function which is 0 on the unsafe set and makes a smooth transition from 0 to 1 as it goes from the unsafe set to the outside of the sensing region. So it sort of makes a smooth transition from 0 to 1 inside the sensing region. Okay? So that's, if I want to sort of project it in a one-dimensional plane. So if you think of this as an obstacle set and this as a sensing region, then it will kind of make a smooth transition. So it will be 0 here and make a smooth transition from 0 to 1. So it will be 1 here and 0 here, right? So this is my obstacle set. This is my sensing region. Okay. So that's the kind of construction we're going to do. Okay. And what is a v? V will be some distance function. Okay. So v will be some distance functions which will tell you what's the distance between the current state and the target set is. So for example, if you're in Euclidean spaces, which is what we'll be doing, like in Rn, then you can take v of x to be simple distance function. Okay? This is like your psi of x, the projection of it from the one-dimensional, and v of x is a distance function. Okay. For x in Rn, one can pick v of x to be equal to x minus x of t square. Okay. Now, how do you construct the psi of x? I think like you can construct psi of x in multiple different ways, because as I said, the characteristics of the psi of x is 0 on the unsafe set and then goes from 0 to 1 in the sensing region. So now you can look at some books and how to construct the psi of x as a smooth function which do some with these characteristics. And one of the construction is the following. So you start with some elementary functions. So I first define what this f of tau is. So f of tau is an exponential of -1 over tau. So these are all the details. Okay, I'm now giving you the details. So if you don't get those details, that's okay, because there is no sort of a unique way of I mean, there could be different ways of constructing it. As long as you sort of get this main picture, the big picture of what this function should look like. Now, there could be various different ways of actually constructing this. I'm just telling you one possible way of constructing it. Okay. So, so we are basically trying to construct what is called as the inverse bump function. Okay. So if you know what a bump function is a function which is kind of actually 0 everywhere, and then it actually bumps up and then goes to 1 smoothly. And then again, it sort of goes from 1 to 0, right? So it's like a bump function. What we're trying to do is actually we're trying to construct the inverse of that, right? So that it is sort of goes to 1 and then kind of goes to 0 and then goes on 1 again. Right? So these are the basic ingredient in this construction. So using this f of tau, one can define another function called as f bar of tau, which is given by f of tau divided by f of tau plus f1 minus tau. Okay. And then we do now I define, so I think these are, as I said, these are all the details. So phi of x, now I define some new function. So I'm sort of constructing this function in step by step. So I first define f of tau, f bar of tau. Now I define phi, and then I'll define the psi, which is the function I really am interested in constructing. So what is this phi looks like? The phi looks like the following. So phi will be a function which is 0. So what is that I'm ensuring when I'm actually doing this construction? The first thing I'm ensuring is I want to ensure is that these functions are actually a smooth function. They're C infinity function. Just because I'm going to take the gradient of this function, positive gradient of this function when I'm trying to design the feedback control. So that's the ingredient in this construction. So phi of x is 0 for x belongs to the unsafe set. Phi of x will be equal to f bar. So f bar of so instead of tau, so notice the tau here is a real number. So instead of the tau in the argument, we use h of x minus s of x. So remember, this h of x was the function which described the unsafe set, and s of x is a function which describes the sensing region. So this is what you use, and then it is 1 when x belongs to the sensing region, and it is 1 otherwise. Okay. So this is the function which actually does the smooth transition from 0 to 1. So it's 0 on the unsafe set, and it makes a transition from 0 to 1 in the sensing region, and it's 1 outside, right? So this is okay. So this is 1 outside here. Okay, so that's what it is. Now, what is your psi? Psi of x is constructed at some phi of x plus some theta, where theta is small positive number, and this is something that is important to use in the proof of this, because I think the important thing about uh, the main contribution here is actually to prove rigorously that if you do construction like this, and if you design the controller with this density, then you can guarantee almost everywhere navigation. Okay? And that proof is, that proof I think is unique. Okay? So this theta is a small positive number which is used in the proof. Okay? And okay, so with this, now you have this rho of x, and then you can do this psi of x divided by v of x power alpha. So what are the parameters? So what are the parameters in this construction, right? Because there are if you forget about this if you forget about this construction, there are two main parameters in this, which is theta and alpha. Okay, and then there is also a third parameter here, because all that is given to you is the description of the unsafe set, right? That's what is given to you. What are the external things that you have introduced? The external thing that you have introduced is the sensing region. So sensing region is something that could be tuned, or that could is a tuning, is sort of a tuning parameter which you can actually tune to make this algorithm work. Okay, but other than the sensing region, which is the capture in this function sk of x, s of x, you can also think of this s of x as just kind of actually enlarged version of the h of x, right? Because h of x is already captures the geometry of the unsafe set, so you can actually enlarge the h of x to get the s of x, because you want this sensing region to be surrounding this obstacle set. So s of x, in that sense, one simple construction of s of x, the sensing region will be as I said, is just a annulus around the obstacle set. Now, if it is just the annulus, then it's just like a fattening of the unsafe set, right? So in that sense, s of x can be constructed from h of x with the sort of a distance of the sensing region as a parameter, right? So if I want to draw that, so this could be a tuning parameter, right? Which is the region where the width of the annulus, basically, where the function makes a transition from 0 to 1. Okay, so these are the kind of a three tuning parameters: theta, the distance of the sensing region, or the radius of the sensing region, or the diameter of the sensing region, whatever you want to call it, and the alpha. Okay, so what does this alpha does is actually this alpha is actually, so if you make this alpha very large, so think about 1 over distance function. So let's say if your target is at the origin, v of x will be just x square. So if you have 1 over x square, then the 1 over x square will actually blow up at x equal to 0, right? Now, if you add that power alpha, you can actually control the rate at which it blows up. So if you increase the alpha, it will blow up faster. If you reduce the alpha, it will blow up slower. So what that does is actually if the initial condition is very far, if the initial condition is very far, and since you're taking the positive gradient of the density, it allows, if alpha is very large, then the robot can actually sense where the target is from very far. Makes sense? Because this 1 over x square actually decay very fast, right? So if you, depending upon the value of alpha, it could decay faster or slower. So if it decays slower, then you can actually sense things from further apart. If it decays faster, then you may not able to sense things from far. So that's the role of alpha. So these are some of the physical parameters, or the nice thing here is that all these parameters have a very intuitive uh, feeling or intuitive understanding, because the density function is also very physically has a physical interpretation, nice physical interpretation. So that's the role of alpha. The theta is a parameter, as I said. I think it is introduced in the plays a very important role in the proof, but um, uh, for here, for discussion here, you can think of it as a small positive number. Okay. Okay. So if that's the case, then uh, so once you have this construction, then you just do x dot equals u. Okay. So I mean, I'm trying to design controller for the integrated dynamics. As I said, we're we're just doing the path planning problem. We're not trying to actually do the like when you're doing the path planning or motion planning, we are not accounting for the complicated robot dynamics. So then you use the u to be partial rho partial x, depending upon. So maybe you can take a transpose of this, because this is a column vector, this is a row vector, and then you can show that, and you can. So this is now a dynamical system. X dot equals partial rho partial x transpose. This system will solve. Yeah, so almost every navigation problem, because it will take almost all initial conditions from the in the small neighborhood of the initial state x0 to the target set xt. Okay, it guarantees this in almost everywhere sense. So there may be a one or two trajectories which you cannot, which could go through the unsafe set, but almost all initial conditions can be navigated to the target set. Um, I mean, I don't want to do the proof, but let me see if I can actually uh, actually hook up my laptop on this, or to show some slides. Yeah. So this is this is the paper I want to show. This is the paper which I'm talking about. So here you can see. So what is this almost everywhere, right? So almost everywhere would be like, imagine a case, and this is what is basically trying to explain here. So there may be a few cases. So what you see in this figure 3 is the following. Okay. So you maybe it's not clear. So you think about it, you have a circle, which is the unsafe set, and your target is actually at an initial condition and target are at di diagonally opposite places, right? So, and that's the case which you cannot actually solve, okay? Because that actually creates a saddle point, and the saddle point. So, mm, how should I say? Okay, so what I told you is that when you do this navigation function construction, right, what you end up actually is creating local minima. Okay, so whenever you have local minima, you also have what is called as a saddle point. So what are the difference between local minima and saddle point? So local minima is like in all directions. It's like the gradients are actually the second derivatives are actually positive, because it's like a local minima. But then there are some saddle points, which are unavoidable. So they are also created where for a saddle point, and along certain directions, you can actually, like, it's a saddle. So along some directions, you're actually going down, along some directions, you're going up, right? So while this algorithm actually ensures that there are no local minima, of course, like no local maxima, because it's exactly opposite, but you can still have this saddle point. And the saddle points are precisely the point from where you cannot guarantee the navigations. Okay. And these are actually forms of measure zero set, because it's very difficult to get to the saddle unless you ride along the stable direction of the saddle, and which is a measure zero set. But this example, you see, is, I mean, this case is exactly the case when you're actually sitting right on top of the stable manifold of the saddle. If you have a scenario, if you have a configuration where you have a initial point and a final target point lying exactly 180 degrees, where the obstacle is in the center, then you create a saddle where you actually start navigating from here and gets stuck at the saddle. Okay, so that's a sort of a measure zero case. But if you make a small perturbation in your initial set or target set, you'll actually avoid that. Okay, so that's the measure zero. Now, so you see here, what you see here is that you want to actually grow from. So these the gray color boxes here are the different obstacle shapes of the, and you want to get to the origin from almost all. I mean, so you're just picking all initial conditions in the state space, right? So you can see it actually gets successfully to the origin, which is the target set. Now, it's this figure B actually sort of demonstrate that it can actually navigate through a very like a sharp, narrow region, right? So you have this environment which is sort of cluttered with obstacles. You can actually find a nice gap in between these multiple obstacles. Okay, and again here you see in the high dimensional space where this is actually all filled of obstacles, it can actually go to the it can avoid all of them and actually get to the target. So these are the kind of things one could do. And similarly here you see it has like a obstacle which consists of a torus, a cylinder, and kind of a curved cylinder, and it kind of goes through this maze and goes from this black to the green. So green one here is the target, the black is the initial condition. Okay? So things of that sort. Now here you see, this is a good example. So let me see. Yeah, you see what happens here is that there is like a saddle. Okay, so I have to switch this again and again. So this is like your saddle, and then the initial condition is inside the saddle, and your target is outside it, right? So so it's like you're trapped in a prison. You're trapped in this box, right? And you want to reach the target. But if you actually don't have, so the natural action to do if you're trying to just go in the direction of a target is actually to hit the wall, right? Because that's actually the closest distance. But the smart thing to do, because there is a wall right in between the initial state and the target, you have to sort of take the longer route, right? So this is what happens. I mean, I think depending upon the different sensing region and different tuning parameter in figure A, so the R1, R2, these are kind of this R2 here is the sensing region. I forgot what the kappa is. Yeah, so the R. So yeah, this R here is the sensing region as described in. So by changing the sensing region and so on, you see you can actually get to the so in the figure A, you see they kind of this initial condition actually sort of move by hugging the target set and getting to the hugging the obstacle set and gets to the target set, and then and yeah, so you see these different behaviors in the figure B. You see that they actually first, I mean, they kind of disappear. So in the figure B, these are not able to successfully do that because the right set of comparison of the density function and navigation. Okay, so this plot, okay, good. Okay, so the two figures on the left. Okay, so the kappa is one of the tuning parameter for the navigation function, right? So I was telling you about this navigation function. So these two figures on my right are actually the plot correspond to the navigation function, which is the way you actually do this in the primal setting. So there you see on the figure B, it actually never is able to get back because they actually just shoot off to infinity. In figure D, by proper tuning, they are able to get to the target, but then first they have to sort of go very far outside before actually. So the way you visualize this is it actually goes far outside and then you come back here. Okay, so you are going very far outside before actually reaching the target. And in this case, they just goes off. They never come back. Right. So here it kind of goes off and they never come back. Whereas in these are the two, one which obtain using this density approach, where by tuning this radius of sensing, so here you see they kind of actually hug along this obstacle sites and actually get to the target. And yeah, so here I think maybe they are not successful, or it doesn't converge. Yes. So in this case also you have a case in scenario where they're not able to converge to the target in the figure A, but by properly tuning the radius of the sensing, they are actually able to get to the target. Okay. But in both the cases, they never actually, the trajectory never fly off to infinity. The trajectory never goes very far before actually getting back. Okay. So kind of moves around the obstacle set. So yes, things like that. And then you can also use this to do kind of look at applying this densities on more complicated dynamics involving this like a manipulator, which has non-trivial custom dynamics. But then this is not something which is sort of surprising, because this is sort of done very routinely in the robotics communities. You design controllers, especially for things like this manipulator, where you can actually use inverse kinematics to sort of design this low-level controller to execute any to execute a trajectory, or rather to get the system move along a trajectory, right? So once you have this safe trajectory, you can actually then design a low-level controller using inverse kinematics for the systems like this to track any desired trajectory, including the safe trajectory. So that's what is shown here. So that's one of the way to actually extend the applicability of this density function, which are designed based on a simple integrated dynamics to more complicated dynamics involving using this inverse kinematic kind of thing. Okay. So I think that's one thing. So I think the next question is how do we let me see if I can since I'm here, let me show this presentation as well, because I want to show you the movie, which is, I'm going to talk later. So if yeah. So this is, you can see this, right? So, oops. So here in that algorithm, I showed you that we have a global information of the unsafe set, right? But if you really look at this, the way the controller is actually working, the controller is just going with the positive gradient of the row, and the row has the information about the obstacle set. But what if I don't have a global information of obstacle sets, right? So you're only able to sense the obstacle sets when you're in the sensing region. So what this two figure shows is that these actually are done when I don't have a global information of obstacle sets. I only sense them once I enter the sensing region. Okay. Now, what is the effect of actually changing the sensing region? That means if I make the sensing region large or small, what happens? So the two things. One is I don't have a global knowledge about this obstacle sets. Second is I can actually sense them sooner or faster. So this is what happens. So in the figure on the left, you see you have a sensing region which is very large. So what if we have sensing region very large, then the trajectories are sort of very conservative. They actually tend to avoid the obstacles right from the beginning. But what if I actually have sensing region which is the case on the figure on the right, when the sensing region is very small, then you see that it kind of actually gets very close to the obstacle before actually it sort of avoids it, right? So it can then kind of go through this narrow region. Okay. You see it gets close and then it avoids, and kind of again go. So you want to go from this red dot to the green dot, right? So red is the initial state, green is the target state. Whereas in this figure on the left, it actually senses way ahead and then just completely avoids the entire clutter of the obstacles, doesn't even bother to go from inside. Okay. So you see, this is kind of this is what you'll expect, right? This is what you'll expect. And the nice thing about this is that all these things are very intuitive. Okay. The next slide, actually, I could just show you now, but I think this is kind of the thing I want to talk. Like, I want to talk about two different things. Is that how do you extend this to a more complicated dynamics, and second is how do you do it in the dynamic case. So for the figure, what you see here, the figure, this is when the unsafe sets are actually moving. They are not stationary anymore, right? You want to go from the top to the bottom, whereas the unsafe set, so the gray circles are the unsafe set. They are not stationary anymore. So they're kind of moving around. So you see, as it gets close, it gets repelled, right? And yeah. So it's kind of fun because this looks like some emergent behavior is kind of uh, like, yeah, some behavior is sort of emerging, right? You just design the simple laws. Um, so what is the difference between this and the static unsafe set is that in the static unsafe set, maybe when I go back to the slide, I'll tell you a little more, but in the static unsafe set, the all you have to do is basically you have to change the h, right? So in the static case, h of x is actually not a function of time. So in the dynamic case, you make h as a function of time. That's it. Okay? And then again, you can actually do it without the global knowledge of the dynamic environment or just the local knowledge based on local sensing. And for the figure on the right, I think it's even interesting. So here, the target is actually moving. Okay, it's not stationary. So you see what happens. The target actually goes through the unsafe set, but the robot actually stays outside. And then it'll wait until it exit the unsafe set before actually catching up. Okay? So it doesn't follow the target in the unsafe set because it has to stay outside the unsafe set, right? So it kind of hugs, it stays close, it hugs around the unsafe set, and so in the second case, it just waits until the target actually exits, and then it catches it again. Okay, and once it goes outside, it just leaves it, right? Because then it's not in his in a safe region. So this the two lines, horizontal line is actually the safe region. So once the target actually goes outside these two lines, it just stops. It just doesn't try to trace it. See, it catches it there, and then it goes out, but it just stays inside. Okay. So I think all this cute little thing one could actually do with this, and yeah, I mean, if you guys can think about a good applications for this, I mean, one could write some neat papers. I haven't dwelled onto the application side of this. I just dwell mostly on the apply. So one of the very nice applications of this is actually when you are actually trying to do, let's say, you have vehicles, right? So this is sort of very common in India, but not so in US, where we don't have any stop signs, right? So we get to the intersection, especially in the small cities, you get to the intersection, and then the vehicle just sort of no none of the vehicles stops. They just slows down at the intersection, and everybody sort of goes to the right. Like vehicle from the left may want to go to the right, from yeah, right. So they can actually mutually sort of coordinate without a stop sign, right? So, one could think about designing algorithms for scenarios like this using this, right? So, where the other vehicle is like a obstacles. It's like a dynamic obstacle, right? So you have like four vehicles at the four corner uh, of the square, and then they want to go to the diagonally opposite end. um, can they do it without having a global information, right? So that's exactly the scenario where you can treat each robot will treat itself as the yeah, it's a robot, and then the where the final destination will be the target, and all the other three or n minus one robots could be the dynamic obstacles for the particular robot, right? And then the particular robot doesn't need to know the the global information or the continuous information about all the n minus one robot. As soon as this n minus one robot, any one of the one n minus one robot enters into the sensing region, it can actually execute the this feedback control strategies and it can avoid it. Make sense? Oh, you mean in the practical setting, or I mean, I think you should be able to do the same, exactly the same uh, right? Exactly the same. You mean in terms of like a sensors and stuff, or yeah? I mean that for hardware. I mean you'll have to think, but I don't think that should be. I mean, I think people must be doing it some shape or form right now. I don't think hardware implementation should be. Yeah, I'm I haven't dwelled into the hardware for this stuff, but based on my experience with dealing with other hardware, I think it should be fairly straightforward. Yes. Um, yeah. So, any question before actually? So, what I want to tell you now is yes. So, so there, the sensing region could be just defined in terms of the distance, right? So, so as soon as you get within some epsilon distance of the obstacles, that's your sensing region. So even the sensing region, you saw that it's basically can be characterized purely in terms of the annulus, which is basically the distance to the obstacle site. So I mean that's all you will need. You don't really need to know the whole shape of the obstacle set, which is the sort of information which is used in SK of X, right? So, and that's what is been done here. I mean, there may be some issues when you are sort of dealing with like a very weird shape um, uh, uh, obstacle set, right? So that may actually could trap you inside this, like some sort of a very highly non-convex shape of the obstacles where it can actually trap you right inside the unsafe site, right? Just like we have that horseshoe example, uh, something like that. But yeah, I mean, that could also be avoided by using a very large sensing region. So then you are basically doing sort of a convex hull approximation of that non-convex set. But I think that I found this very fascinating. I haven't gotten time to actually sort of look into more details of this, but I think this looks very interesting behavior. And yeah, yeah. So as I said, the theta is actually introduced in this to actually prove certain things. So what happens in the following? So when theta equal to zero, so what I'm doing is actually I'm using the phi function and then the psi function. Let me go back to this. I mean, theta is something which is used very smartly in the proof. So, um, so if you look at the theta, the where the theta comes and the psi comes, I wish I could navigate this better. Oops. Yeah, so this is the where the theta is actually used. So psi is a function which is zero, identically zero on the unsafe set, and it actually goes from 0 to 1 in the sensing region. But we don't use sorry, phi is a function which is zero. Now, we don't use the function phi, we use the function psi. So psi is a function which is modified by theta. So really what happens is that the psi, which is the function which is used in density, is not identically zero. It's actually, it has takes a small positive value. And that small positive value actually is, I mean, it's it is used in the proof. Let me just stick to that to make some sort of an argument, because when you make that theta equal to zero, actually some of the things doesn't work in the proof. Okay. Um, and I will say, and that's what I'm. So the physical parameters are more of this alpha and the sensing region. Theta is used in the proof. If you go to the proof is fairly long. Uh, you will you'll figure out where the theta is used. I'm using that to make some major theoretic argument to do this thing. So without the theta, the proof doesn't work properly. Proof doesn't work at all. Okay? So so yeah. The next thing is, of course, we have done this now, and this is now where the some of the stuff that we did actually, the approximation linear operators and so on, is actually could be used, will come in useful. Is how do I use this density to do uh, motion planning, accounting for the 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 complicated robot dynamics. Okay, how do I sort of extend the utility of this to include um, the drift of the system, like not just for simple integrator, but for x dot equals f of x plus g of xu kind of thing, right? And the idea is fairly simple. Idea is along the lines of the idea of the control Lyapunov function. I don't know how many of you are familiar with this control barrier function. So control barrier functions are basically extension of the control Lyapunov function, right? So the control barrier function are like a control Lyapunov function. So where you assume a barrier function and then you use them in a control setting and then hope that it will work. Okay. So similarly, one can now use this density in a control setting and call them as control density function. Okay, and hope that this will work. We just hope. Okay, so in the integrator case, we can prove analytically, rigorously that this construction is going to work. But once you actually use this density function, which is constructed analytically with the drift dynamics in the control density function setting, you can write down the problem nicely. You can in fact write down this problem as a QP problem, just like you write down with the dense barrier function. But just like with the barrier function, we cannot guarantee that it's going to work. Okay, but you can nonetheless write down this as a nice problem. But given that it has much more physical interpretation, much more like the parameters which are physically introduced to tune, at least in simulation, we can show that it is working very nicely. So how do you formulate those problems? Right. So how do you and I use this density function which I have constructed, which for the construction I have just shown you? How do I use this in the um, for system with drift? Okay, and that's basically what you call as the control density function. By the way, I think we also, yeah. I think maybe since we are at this topic, let me just first tell you how to do this construction for the time varying case. If I can find the paper, I think then because that's we don't then have to come back to this again. And I think yeah, it's I mean, there are some more complications when it comes to time varying environment, but as far as the construction of density function, more complication in the proving this time varying environment. But as far as the construction of density function is concerned, it's kind of fairly straightforward. Um, right. So I mean, without spending too much time on that, let me just tell you. So all the changes that you have to make in this is basically, as I said, make the function h of x as a function of time. So h of x, which was the function used to define the obstacle set, that becomes a function of time. And so basically, you can think of that the center of the unsafe set is actually changing with time. Okay. Um, what is what? Preference. I have a papers on this. I have multiple papers on this. So some of them are published, some of them are still no textbook. I mean, like you also dense density functions that I mean these are not in textbook yet. I mean for the navigations and stuff, these are still in papers here. Especially, I mean, yeah, the way we are doing it, this is the first time. I mean, there are general reference on density functions. Yeah. I mean, I think one of the things which I haven't done in this course of the lecture is actually I haven't given you any references, right? I mean, I could start writing them down, other than the first one, right? So, but I think there are especially on the basic stuff, there are a lot of references. I mean, I could good point to some good references. By good, I means credible references. And then I can also point out references which are not credible, but still they are actually does a very good job of entertaining and actually getting the point across, right? So there are all these references. So I can maybe towards the end I could actually talk about that. Since we are in the flow, maybe let's uh, do this. This control density function is also sort of like a parallel to the control barrier function. Okay, so those who know what a control barrier functions are, so they are again used to design safe controllers uh, for system with non-trivial dynamics. So the idea is the following, right? So the idea is that let's say you have a nominal controller, okay, so which actually does like an MPC based controller, which will actually can do follow certain trajectories and so on. But the trajectory happens to go to some unsafe side. So how do you actually design a filter? So this the control barrier functions or the control design based on a CBF are basically a filter which actually filter the controller to ensure that the safety constraints are actually met. Okay? Because if you have a trajectory which a reference trajectory which goes through past the obstacle, you don't want to actually use that controller to because it's actually going through the obstacle. So you want to actually add a filter so that you can actually change the path and avoid the obstacle. Okay, so I don't want to talk uh, when I talk about density function. I think it will become clear. So let's say you have x dot equals f of x plus g of xu, right? So what I told you yesterday was that if I want to design this controller for stabilization, then that becomes a convex problem in this dual space. And then the condition for that is given by f rho plus g rho u is greater than 0, right? Now, for control density function, since the rho of x is constructed analytically, for safety, right? All I have to construct is actually u equal to k of x. So now you have f rho plus g rho k has to be bigger than 0. So what is the rho? Rho is the same rho that we actually I gave you the construction for, right? Now I want to find a k. Now this problem is rho plus divergence of rho k bigger than 0. Okay. So what is the problem now? So I want to find a k such that these constraints are met, where the rho already is defined analytically, which captures this safety requirement, right? So if you are able to solve this, so what does it mean? If I'm able to solve this problem, if I'm able to satisfy the inequality for a k, so if I'm able to find a k such that this inequality is satisfied, then since this inequality is satisfied for a given rho, then I'm solving the navigation problem. So instead of designing the k when f equal to 0, which was what we did, now I'm trying to design the k when f is non-zero with the drift. Okay, so this is it. So if you can solve this, satisfy the inequality for a given k, then you're solving a navigation problem where rho is we already know, right? Unlike what I was telling you yesterday, that the actual stabilization problem. So the stabilization problem is actually simultaneously finding rho and k such as to satisfy the inequality, and that is actually a convex problem. But that rho may or may not have the information about the safety. But now I have encoding the information about the safety in the rho by constructing the rho which is 0 on the unsafe side, and it's maximum at the target side. So safety and the convergence, right? Both is information. So I have to ensure safety as well as ensure convergence. That is, I'm ensuring that I'm getting to target set while avoiding the unsafe set. So both these requirements are encoded in a rho. So if I can satisfy the inequality, then I'm done. Now, if you look at this inequality, this is actually not a finite dimensional inequality. Okay, because to find the k is actually coming through the gradient. Okay, so now how do I convert this infinite dimensional inequality to a finite dimensional inequality? So that's the thing. So how do I convert this to a finite dimension? So the way you do that is mm, so what you do is you can then parameterize this k of x using some basis functions. Let's say alpha k, psi k of x. So psi k's of x are some basis functions. And then plug them here. And then you convert this to finite dimensional inequality in terms of the alpha k. So this you can write as some alpha transpose psi of x, not to confuse that with this psi. So we use the psi there as well. So let's just use a different notation. Okay. Now, if you plug this in here, you get so now this is basically so this is I'm just using this notation as a vector notation, but so what is this? This is basically uh, okay. Now this is the finite dimensional inequality to find alpha. Okay, in terms of alpha. For a given basis function. So with since the basis functions are known, everything here is known. So you know the g, you know the rho, which you construct analytically. We know the phi, which are the basis functions. We can compute this. F is known, rho is known, so we can compute this. Now we can try to solve this in terms of the coefficient of alpha. So this is easy, the finite dimensional linear equations. Okay. So this is how one can actually extend the applicability of this to large class of systems, especially system with drift. Again, actually, you can. So one of the difficult problem to in robotics is also how to do this thing, safety with robustness, right? So what does it mean by robustness? I'm just going to say things without sort of writing it. So by robustness, you mean like I don't the vector field is has some uncertainty, so you don't know the exact vector field or you don't know the exact system model. So you want to make the navigation robust to the model uncertainty. That is sort of like with any other method. I mean, that is always the case. I think the more important robustness problem has to do with the fact that uncertainty in initial condition. Okay, because you can never sense things perfectly. You never know where you are, so you'll always have some uncertainty in initial conditions. So how do you actually design these things when there is an uncertainty in initial condition? Uncertainty in model and G, I think it's very easy to do for those who knows a Lyapunov function. So once you have a Lyapunov function, it actually guarantees certain degree of robustness. So same thing with this as well. It guarantees some degree of robustness to modeling uncertainty. So same thing with this as well, because because we are trying to make this quantity bigger than 0. So if you have some f which is different than the 2f, then instead of making it bigger than 0, you just want to make it bigger than some positive number, because that will actually make it robust to any modeling uncertainties in f and g, right? But so that's very easy to do. The the robustness to the initial condition is hard, okay? Because there you want to actually not make sure that the controller that you end up designing will not work for the given initial condition, because this controller that you have is actually a function of the states u equals to kx, right? So this is what you will end up at the end of the day. So u is a function of x, but you may not know the x. I mean, you may not know the precise x. So you want to actually make sure that the controller that you end up design actually will not just work for the current x, but will also work for a x in some small neighborhood. So basically what you're asking is that the control that you end up implementing as a function of x is robust to any uncertainty in initial condition. And I think that is actually more challenging problem, because then it actually becomes um, uh, so this, if you look at this, this is actually a finite dimensional. I mean, this to begin with was an infinite dimensional optimization problem. After this parameterization, it becomes a finite dimensional optimization problem. But now, if you want to actually build some robustness to the initial condition uncertainty, this again becomes an infinite dimensional optimization problem. So that's where the challenges arise. And I think there are ways to actually do this. I'm not going to details of that, but I think those are some interesting problems one could actually further look at, or extension of this in terms of robustness to initial condition, robustness to modeling uncertainty, and so on, which are very practical things to do when it comes to the robot application. So let's have. So I think this may be, it's 10:30. So this may be a good time for a break. So what I'm going to do now is I'm going to switch gear a little bit. In the next half, I will tell you how the Koopman theory could be used to look at some low-level control problems for robots. I mean, part of that I feel is also the way we kind of went so far as the Koopman data-driven control is concerned, was very abstract, right? So it's a sort of, I mean, we didn't really have much time, but we covered some basic things, and I gave you some basic algorithms, vanilla algorithms of how to go from data to model to control, right? Now, of course, one could say that I could do the same, I could execute the same pipeline for any robotic system, right? But devils are in the details, and you could do that, and I think you could be successful, but I think many times it doesn't work. And I'll tell you, like the lessons we have learned, and then what are the challenges that arise when you actually try to apply this, develop this pipeline. So what we have actually within our research group, we have this uh, uh, the pipeline which can actually take data from simulation model, from real experiments, develop this Koopman model, and do some sort of an adaptive Koopman based MPC, and show that it's working on the hardware. Okay, so it's kind of goes all the way. Then of course it's I cannot take credit for any of this. Okay, because it's all hard work by the graduate students, and it kind of requires a lot of painstaking efforts of tuning this, curating data. So kind of things we actually have taken for granted in this lectures, in terms of, oh, we have this time series data, or we take this time series data, construct this. I mean, even coming up with this data, collecting this data, synchronizing this data is actually the challenge. I mean, it takes months to get the right data, because I mean, if you have bad data, there's nothing you could do, right? So it's one thing to say that you take this data, construct this model, but what is the data? What is the right data? What's the right sampling? What's the right synchronization? This data is actually coming from different sources. So how do you sort of timestamp them? How do you synchronize them? Things of that nature. So on one hand, I may not have much to say, but at least because as I may not have much to say in the sense of this, most of the work is done by graduate students when it comes to all the data collection and so on and so forth. But at least I can tell you what are the errors that were made, or what is the and again, this is sort of again very problem specific. By problem specific, I mean like particular robotics platform you're working on. So the platform that we worked on was the two different platforms, the wheeled, vehicles on the off-road terrains and the quadrupeds. Right? Um, and yeah, so these are sort of the experiences are kind of limited to these two. But I think there are some things that I feel, and I spoke about that a little bit yesterday in terms of actually like the way to think about this systems interacting with the environment, which perhaps could be actually applicable to other robotics platform as well, right? So how do you think about system with interacting with environment in this Koopman setting? So yeah, so we'll talk about that after the break.